Hey guys, today in this video we have the infinite square wave solution for dimensional quantum mechanics problem. So we define the square wave, infinite square wave, that is v of x equals to 0 for x between 0 and L. So v of x is infinity outside the veil. And you can imagine this veil like that. So this is just a visual representation of it. So we write the time-independent Schrödinger's equation for the infinite square veil, which is the following: negative h bar squared over 2m d squared psi over dx squared plus v of x psi, which is equal to e psi, where psi is the wave function, h bar is the Planck's constant, a reduced Planck's constant, which is also called Dirac's constant, which is the Planck's constant over 2 pi, so h over 2 pi, and m is the mass of the particle that we are worried about. Inside the square veil, the potential energy is 0, so v of x is 0. Thus, our equation would simplify to a very simple differential equation, and it would become d squared psi over dx squared plus 2m e over h bar squared psi to be equal to 0. Now we can define k squared here to be 2m e over h bar squared. And if I replace this thing right here, I'm going to be getting d squared psi over dx squared plus k squared psi is equal to 0. So that is just an ordinary differential, not ordinary, that is just a differential equation that has already defined solution, which is the following. The solution, the general solution of psi in this kind of equation, psi prime plus k squared psi is equal to 0. The general solution is psi of x to be equal to a sine of kx plus b cosine of kx. Now we have to apply the boundary condition at x equals to 0. Psi of x is equal to 0, we know that. And if we replace this boundary condition, 0 is equal to a sine 0 plus b cosine of 0. Sine of 0 is 0, cosine of 0 is 1. Therefore, we get b to be equal to 0. Psi of x, therefore, is a sine of kx, because b is equal to 0, as we derived it from our boundary conditions. Now apply the second boundary condition, which says psi of L equals to 0. Therefore, a sine of KL is equal to 0 for non-zero wave function. So, in order to make this expression equal to 0, we have to have KL to be equal to n pi, where n is equal to is some integer. And we're gonna get Kn to be equal to n pi over L, where n, as I told you, is some integer. Now we have to determine the allowed energy levels. We get E equals to h squared k squared over 2m. En is equal to h bar squared over 2m n squared. Pi squared h bar squared over 2m L squared. Now we have to normalize our wave function. So we can normalize it by integrating it from 0 to L by squaring the wave function and integrating with respect to x from 0 to L, which is equal to 1, to find the constant a here. And you must know that is actually our integral is actually psi conjugate times psi, but because our wave function is real here, the psi conjugate is going to be psi, so we have psi squared, which is the following: a squared times the integral from 0 to L of sine squared of n pi x over L dx is equal to 1. Solving this integral would give us a to be equal to square root of 2 over L. And if you want to find the final stationary eigenstates for the wave function, our solution is psi of n to be equal to root 2 over L sine of n pi x over L, where en is equal to n squared pi squared h bar squared over 2m L squared, where n is integer, as an integer. So I'm going to show you here the first 3 eigenfunctions graphically. So this is where n is equal to 1, n is equal to 2, and n is equal to 3. So therefore the infinite square value psi n of x is equal to root 2 over L sine of n pi x over L, and e of n is n squared pi squared h bar squared over 2ml squared, which shows us that energy is quantized, and that's where the word quantum comes from, because energy is quantized in quantum mechanics. And that is the easiest form that we can represent the solution for infinite square value. Hope you enjoyed this video. Please make sure to like and subscribe. Tell me if you like the animation, this style of video, and I'll see you next video.